So I think we had talked about these last week. We have these two assignments that are currently out there due on the 22nd. You can probably start chipping away through most of that individual assignment based off what we did last week. Also, I got the slides reposted from last week. So the completed version of the slides have in the log, normal, and the exponential stuff. Someone, I didn't realize prior to class that I had uploaded the one that didn't include it. So you'll have all of that as kind of resources and references to go back and look at as well. Other than that, any questions before we kind of jump into some new material here today? So I put up, you don't have to go through it, but I put up kind of the next subject we're going to be going over, that kind of Learn Smart or Smart Book, whatever they call it. Just kind of walks you through, kind of gives you a glimpse into things that we're going to be talking about. But today shouldn't be too bad of a class. I think today's I like this class period. So we'll be talking about sampling. So we, ideally, talk about all these distributions, but they've all really been thinking about it. We can look at the population data. More often than not, we can't, right? All we can look at is sample data. So we want to make sure that we get a sample that looks as much like our population as possible. So I have two situations in which we'll be sampling. One, we have a finite population. This is going to be pretty much every example that we think about. And you could look at an infinite population. This is going to be something like where there's probably more of a, this would be something that the computer is creating these different outcomes for this random variable x, right? And it's going to be kind of doing it for here at the end of time. So right, we have an infinite population. That's not very common. Often we're kind of looking at this finite population example. So we need to take a sample. It's not usually very feasible to get every single member of the population because something like a census is very expensive, and it's probably only every 10 years. It's also just practically hard to go out and gather data for the entire population of every single thing you want. And every time you want some information, you do a new census. That doesn't make a whole lot of sense. So we've got this sample. We're then going to calculate statistics from it, and then use those statistics to make inferences about the population. So if I'm interested in the average income in the US, I'm going to have to take a sample, calculate the average income of that sample, and say, based on the sample I took, it looks like the average income in the US is this. Right? I'm making an inference about the entire US population just based off my little sample. So you can kind of imagine some things that might go wrong. Right? What if my sample tends to have individuals who are older? Well, as you progress through life, quite often your income values tend to get higher. Right? So then my sample would be a little bit biased. Right? The average of my sample wouldn't be very reflective of what the entire population of the US is averaging. So I might run into some of these problems, and we'll kind of talk through a lot of them today. So we'll start calling our population, right? Well, I guess we have been calling our population capital N. Right? That's our population size. And we're going to take some subsample of that, lowercase n. So what we need, we'll have two different ways we can do this. We can sample with replacement. So this would be like if I put all of your names in a hat, right? And I only want to get a sample of 3 of you. I draw a name out of the hat. I write that name down. I put it back in the hat. I shuffle around. I draw a name out again. Write that name down. Excuse me. So I'm replacing the name every time. So what's a potential problem I could end up with, especially in the example I gave, like a small class like this? I'm drawing out 3 names, but I'm putting the names back every time. I could draw out the same person, right? So doing this with replacement, I might end up with, in my sample, one person might be in there twice, but everybody else might only be in there once. So often we do this without replacement, right? Once I kind of select a certain observation or a certain person or a certain company, whatever the example is, I can't select it again. Right? I make sure that every individual in the population is only in my sample at the very most one time. Right? They're either not in it or they're only in it one time if I do it without replacement. So I don't, there's probably arguments for some things doing it with replacement. It's almost never going to be the case that that's the only thing to do. At least in the context of kind of applied statistics. I'm sure that there's some theoretical stuff where you might want to start doing something, but For us, mostly without replacement. I say it's better. It's probably not good to say it's better. In most situations, it's a more appropriate way of selecting your sample. So if we had an infinite population, we would do the same process. So every element or every observation would come from the population. We need to make sure that they are drawn independently. So getting one individual, doesn't change the probability that I see another one. So even though I'm talking about this in the terms of an infinite population, you can imagine in a finite population, we don't want this to be broke, this rule to be broken either. And somewhere where we might see this is if I choose, like, let's say I'm sending out mailers, it's really hard to get people to respond to like letters or even emails, right? But if I get someone to respond, maybe I then ask them, oh, okay, good, I got someone who's at least going to interact with me. Do you have anyone else in your household who would like to do this survey as well? Well, that would break the independence rule because getting that person to respond now makes it more likely I see people within their household as opposed to just any other random person. And the problem with that would be people who are in the same household, especially if it's like kind of the same family, well, their characteristics are likely pretty similar. So now I'm kind of like over representing whatever those specific characteristics would be. So how can we kind of make sure, so once we make sure we're not kind of breaking this rule of independence, right? We're not like asking for other people in the household. We've got some other issues as well. So let me think about a good example here. Okay, so maybe I want a sample of 100 people. That's all the people I'm going to go out and sample. And I'm interested in, I'm doing an easy one. Let's say I'm interested in average height, of the US population. Okay, so average height in the US. If I go out, take my random sample, and I end up with 70 males and only 30 females, just by happenstance, what's the problem with my sample going to be relative to the population's average height? The population has about 50% male, 50% female. I mean, around that roughly. If my sample has overrepresented males, then the mean I calculate from that sample, that average height will be higher than probably what the population is, right? Because I have a characteristic, a demographic characteristic of my sample that doesn't match up with the population. If I'm interested in, well, I'll finish this example and I think I've got one more. So I know that I want my sample to kind of have a 50-50 breakdown of males and females. So what I might do is something called stratified random sampling. So I divide my population up into two non-overlapping subgroups, or something called strata. Right? So what I could do is say, well, look, I want a sample size of 100, but I know that for height, gender plays a role. So I'm going to go out, randomly select 50 males, and then randomly select 50 females, and then put them together to get my total sample. Okay? So we'll select a random sample from each one of our strata. Here it was easy, like we just broke it down, male, female, 50 males, 50 females. Then I'll kind of combine those two random samples together to get my full sample of 100 people, which I now know has a gender breakdown very similar to the average or the US population. Another thing I might want to do is, I don't know, what's something that old people do? Oh, maybe I'm interested in the average healthcare expenditures of an individual, right? Well, if my sample, right, let's say, and I'm doing a survey around a college campus. Well, then I know my sample is going to have individuals who are relative to the average person in the population, who are much healthier, right, as college students, right? As people get older, right, they tend to increase their health expenditures or their healthcare expenditures, right? More things start going wrong, right? You need more surgeries, So I might want to make sure that my sample matches the kind of age distribution of the population in the US. So maybe I randomly select 10 people who are between age 10 and 20, 10 people between age 20 and 30, 10 people between 30 and 40, all the way up to 100 or whatever. Then I'll have 10 samples of size 10, put them all together. I get my sample size 100, and I know that its age distribution will look similar to the population as a whole. Right? That's another example of kind of how you would do this stratified random sampling. Does that make sense? All right. So, often we do this when we know that there's a certain characteristic that is closely related to the variable we're interested in. That's why I think I always use the gender height one. That's pretty easy. Age, healthcare expenditures is another good one. You know that these characteristics will influence the variable you're looking at. So you want to make sure that whatever characteristic that is, it matches up with the population. So usually this is like age, gender. A lot of times we'll see this done kind of in income brackets. So that we make sure that we have kind of the average income in the US, or sorry, not the average income. We want to make sure that we have our income distribution, our sample, match up with that of the US. So the other one that we'll do is cluster random sampling. It's the exact same idea, but instead of breaking it down by a characteristic, we're breaking it down into just like small subgroups. So maybe like with clustering, I do something like, I am going to, maybe it's just more practical. Maybe I have some organization and we're located in like 4 major cities, right? So instead of trying to do random sampling for the entire population, I might do 20 people from Chicago, 20 people from New York, 20 people from LA, 20 people from, I don't know, Houston, 20 people somewhere else. And then from those 5 samples of 20, combine those to get my final sample of 100. So it's really just kind of, instead of breaking it up by a specific characteristic, it's like you're just sampling smaller subpopulations, right? There could be overlap in some of these populations, but you're kind of getting like a small scale version of the entire population as a whole, doing this for different clusters and then kind of combining it. So it's really the same, very similar procedure. Probably use this a lot less than we would stratified random sampling. And a lot of times we see this in kind of geographic breakdowns, right? So I kind of mentioned like you're looking at 5 different cities, or maybe I want a sample size 100, and I want 2 people from every state, right? So every state is kind of a subpopulation of the entire population. So I get 2 people from every state, throw them all together to get 2 from 50 states would be 100 people. So that's the idea of this cluster. So I'm not really like quiz you or anything on the definitions here. We're just kind of setting up ways to start thinking about how we can eliminate bias, right? Because if I don't do this cluster stratified random sampling, I might end up with a little bit of bias. I might have certain groups overrepresented, right, relative to what they are in the population. So a good example of this would be kind of like almost a combination of cluster and stratified random sampling. Is whenever we look at like political polling data, and we'll start to see a few more examples that deal with like these political polls because they're really interesting. Not even just political polls, but like public opinion polls. So I wouldn't want to have like one area of the country overrepresented. But I also know that like if I look at the population of California, it's much different than the population of Rhode Island, right? So what I might want to do is break up the US into regions, right? So I have like the West, the Northeast, the Southwest, the Midwest. And I then would kind of sample a certain number of people so that the percentage breakdown, like the percent of people in my sample from the Midwest, looks similar to the percent of people of the entire US who live in the Midwest. That was a mouthful, right? Or making sure that I have a percent of people that live in the West match up the percent of people that live in the West for the entire US. So it's pretty practical. Like we see this applied a lot when we're getting these samples to make sure that I have like every area kind of represented either equally or represented for whatever percent of the total population they make up. All right, so all this to be said, kind of setting us up for this example we'll kind of use for the rest of the class today, which is that we have this sample, we're going to calculate things like the mean from the sample, and then use that mean from our sample to make inferences about what the population is. So what could possibly go wrong, right? So there's this kind of great example that someone wrote a paper on and allows us to think about a couple main biases that exist when we take a sample. So the 1936 election, the guy running against FDR was named Alf Landon, which we should bring that name back for sure. But I've never heard of this guy, by the way, in all of my schooling, any history class, I've never heard of Alf Landon. So maybe that speaks to the public school system. But right back in this election, there's has anyone ever heard of the Literary Digest before? My grandma had got this little thing, like it used to come in the mail, and she was still getting it like in the 90s, right? But like it basically was like kind of what's going on in the world. There's a ton of advertisements for products, but way back in the day, right? It was pretty popular right before TV and things like that. So they sent out to their subscribers essentially 10 million survey cards. So their hope was if everybody sent back the survey card, right, you'd end up with a sample of 10 million people. That's a big sample, right? From that sample, you could probably figure out which way the country was leaning for the upcoming election. Right? So there's a lot of places that try to do this now, like online, but back then they had to do this with these mailers, these survey cards. So they got 2.5 million people to respond, which you guys probably haven't done any like survey design, or probably haven't talked too much about how to create good surveys in any of your classes. You might in some of your marketing classes start talking about that as you get to kind of higher level marketing courses. But 25% as a response rate to surveys is great, right? Like that is unheard of, right? So this is really good. They get 2.5 million people in their sample. They should still have enough people to predict the upcoming election. Right? So the responses predicted a landslide, 57% of the popular vote, and then the electoral vote would be 370 and 161. However, right, they actually predicted it was going to be Landon who won. Now we know what actually happened is that Roosevelt won. Not only did he win, he would actually won the landslide, right? 523 of the electoral votes, which is like unheard of. Right? This is a wild. I don't know. My history knowledge isn't up to snuff enough to know if this is the highest ever, but I imagine it's ranks up there pretty high. Right? So how did they get this so wrong? Right? How did this survey of 2.5 million people? How was it so far off of what the population was thinking? Obviously, they're stupid questions, but math areas, population versus sample variance, those are stupid. But here's an actual interesting. What if I somehow only sent these to Republicans? So Alf Landon was the Republican candidate at the time. So if somehow when I sent these 10 million mailers out, what if 8 million of them went to Republicans and only 2 million went to Democrats? Well, I know that at any point in the country, yeah, it skews a little bit left and right, but we're close to a 50-50 breakdown. The very most, sometimes like 60-40. We look at the popular vote in presidential elections. So if I'm over mailing these to Republicans, it's going to be more likely I get Republicans to respond. My sample is not going to match up the US as a whole. Maybe Republicans are just more likely to respond, right? So I sent these 10 million mailers out, 5 million to registered Republicans, 5 million to registered Democrats. No Democrats sent them back, and 2.5 million of the 5 million Republicans sent them back. Well, that wasn't my fault. I sent them out equally. I just got a bad response rate from one of these groups. Okay? So both of these things actually you can think about as biases, right? So this first one, where I was talking about sending these mailers or survey cards to a higher percent of Republicans, that would be a selection bias. I was over selecting one group in my sample. Right? Non-response bias would be that, well, if the Democrats just sent these mailers back at lower rates, right? This was my non-response bias. Now I'm just going to end up with more Republicans in my sample, not because of something I did, but because the one group isn't responding at as high of rates. So we've got this selection and this non-response bias. Okay? Now we can usually fix the selection bias. It's hard to fix a non-response bias, right? You can't the problem is if you want to try to fix a non-response bias, you might try to use incentives, but now that you're using incentives, maybe you're getting a different answer or response from the group that you're giving incentives to, right? So it's kind of hard to fix the non-response bias. I don't want to say anything else here. I think we're good. So these are our two biases that might exist. So how are these mailers sent out? And maybe thinking about how these biases kind of actually came about in this specific example. So the way that these mailers were sent out, the way they got these 10 million names, was they had this cross-referenced list where the people on the list were individuals who had both a telephone, right? So their name was in the telephone book, and they pulled from every state's. Oh, here we have the BMV, but like in Michigan, it's called Secretary of State. But basically, like their automobile kind of Bureau of Motor Vehicles, whatever. They pulled names from them as well and had all these different car registrations to then looked at what names were on both of these. That kind of told them, okay, this isn't just like a person that was made up, right? We have a civil name we can match. So the only names that they sent mailers out to were people who were in the phone books, right? Someone who had a telephone in 1936 and someone who had a registered car in 1936. So why is that going to be a problem? Yeah. Yeah, if you owned if you had your own telephone line and you owned a car in 1936, you were very wealthy, right? And so we're gonna by byproduct of how they sent these mailers out, right? We're gonna end up with a selection bias based off of income. Our sample is gonna have way more wealthy individuals than what the population does, right? And in terms of the percentage. So this was two guys, or he was only a solo author paper. I don't remember. Some researchers looked into this, right, and was able to track down a lot of these original people that the mailers were sent out to. So what they were able to do is look at who the people actually voted for, right? Whether or not they responded to this mailer way back when. But then they also found people who voted in the 1936 election, right, who weren't sent these mailers. So they could kind of go back and say, okay, what percent, right, of people in the survey actually ended up voting for Landon? And then what percent of the people who didn't get sent a survey actually voted? Like they kind of go back and kind of look at them. And even though the people weren't in the survey, they went and tracked down people who could have been in the survey at the time. So if we look at kind of people who who both owned a car and a telephone, right? So these are people that weren't necessarily sent the mailers. This is just people they tracked down who voted in the 1936 election. And then they asked them, did you own a car and a telephone at the time? For those people, 52% of them ended up voting for Landon, right? And that's kind of close to what the digest predicted, right? It predicted that Landon was going to win the popular vote. And based off of this survey of people they found who were at the time, sure enough, that plays out. But notice, if you would have only looked at people who had only a car or people who only owned a telephone at the time, and this is not just income, this starts to play a role with urban versus rural, right? Because at the time, people who had a telephone more likely were living within a city, right? If you lived way out in the country, you weren't going to have your own telephone line, right? So if we looked at only a car, only a telephone, we actually see that 60% approximately of those people ended up voting for Roosevelt. So if we just would have used all the names available, this kind of survey that we sent out would have actually been a pretty good prediction. Still would have been a pretty good prediction, right? Because if they only owned a car or only owned a telephone, we still would have got the accurate prediction that it was going to be a pretty big landslide towards FDR winning. Also, if we go to neither, right? People who own neither of those things, you can see way higher percent ended up voting for Roosevelt. And that's, like I said, based off of like people who are in this neither category, probably, poor individuals at the time, probably more rural. So, by using this method of only names that were in both the car and telephone registrations, we over-selected people who would have ended up voting for Landon. This was kind of part of our selection bias, or their selection bias, I should say. Any questions on this? So what about the non-response bias, right? So maybe I kind of already gave this example, right? But what if, the 2.5 million people that responded were only registered Republicans, none of the registered Democrats responded, right? Well, we can look at that as well. So how would that look here, right? it would have been that Republicans were more likely to send this mailer back. So they went and asked all these people and kind of looked at what was, so this was a, I forget now what this was. Hold on. Oh, I should have refreshed my memory. Oh, so they were looking at some not the mailer from Literary Digest, but some other poll that was done at the time they found a bunch of data on. So they could kind of use that different survey to get an idea about kind of what the response rate of these different groups was. So for people who own both a car and a telephone, right? This other straw poll that they had data on, notice only what? 17% of people who ended up voting for Roosevelt responded, and then 35% of people who ended up voting for Landon responded. So, I mean, people who ended up voting for Landon were like twice as likely to return a survey or a straw poll sentiment. And then if you look at a car only, right, pretty similar rates, but still Landon's higher. Telephone only, Landon's still higher. Neither, Landon's still way higher. For whatever reason, right, the Republican voting individuals were just more likely to respond to a survey. And I think they go through a thing in the paper where they explain it was something like, higher income individuals, which tend to be Republican, just have more available time. If we look at their activity or their involvement in politics, even at the local or state level, they tend to have higher rates of involvement. And so, yeah, when you send them a political poll, they're always going to be a little more likely, right, to respond to it, right? Higher income individuals. If I'm not, if I'm like fighting scraping in some big city at the time, yeah, I don't have time to waste responding to this survey. I got to make money to feed myself or my family. So that kind of, just kind of shows that we also not only had a selection bias, we had a big non-response bias here as well, right? So we were going to be getting kind of hit double with that. Both of these biases kind of pushed it towards seeing that Landon won as opposed to FDR. Okay. Any questions on that example? So it's kind of an interesting example to start to think about these two biases that exist. Some other bias that might exist in our sample, and this kind of, usually this depends on the questions we're asking, but people will lie to you, right? I mean, if I give a survey about drug use, what do you think is probably true about the average drug use in a sample versus the population? It's a lot lower, right? People don't like to tell you that they're using illegal drugs, right? I mean, they also may just non-maliciously lie. So a lot of the times we ask a question, especially when it's something that's like going back and relying on someone to remember. So if I ask you, well, what was your income last year? Well, maybe I can't remember the exact dollar amount. It was, around 50,000. So you just say, I think it was like 51,000. Well, you're not really giving the accurate data, right? You might have made $52,135. So you're not trying to lie, but the data you gave is a little bit off, right? It's a little bit biased, right? The other issue you run into with this is if you ask someone like, how many times did you do something within the last year? Well, let's say I ask you, how many times did you give to, or not, I want to give to a charity. How many times did, I don't know, you not wear your seatbelt in the last year? Well, you're always going to probably like like in your head, you think, oh, I didn't hardly do that at all. When in reality, you might have done it quite a few times, right? So anytime you're asking people to rely on their memory, you might almost be like not forcing them to lie, but they can't recall exactly. So there's some other bias that might exist. There's a huge new area of research, which I have here that people misunderstand the question, but it's not just misunderstanding the question you're asked. The way you phrase the question can elicit very different responses. So I'll try to pull this example when we get there later on and we're starting to talk about confidence intervals and proportions. But in the last election, I saw this thing that Fox News ran, and they asked, or maybe it was CNN, one of them, they asked basically the same question, which was like, how do you think President Trump is doing? This is like right prior to the election. But they phrased it very differently. So one of them was like, in light of recent events and like kind of listing these negative things, how do you feel he's doing? And the other one was after, listed some good things, and then how do you think he's doing? Well, just kind of listing positive versus negative things, the difference in the like favorability of his presidency, there was like a 12-13% difference, right? So just phrasing the questions differently, you can elicit very different responses. So what you want to try to do is not bias your results by like this positive or negative framing. You just want to ask, what do you think of it? You just want to ask just the question, right? So even just how you ask the question can sometimes influence the results. So let's look at this and we'll kind of think of it. So I'm going to ask you to use your eye clickers here. And I think this will be maybe a helpful thing to start thinking about all these biases in some slightly different contexts. So if I were to ask you today to rate your health from 1 to 4, respond with what it is. I won't look at any of these results, by the way. It's just to kind of have a thing. I don't, Don't think too hard. Don't overthink it. There's no right answer here. So is there 12 of us here because we're missing 1? 13? All right. Close this out. So let's look at the results. Okay, so most people are 2 here. Just a couple, no, someone's not feeling good today. So, right, we've got these different health ratings. I just found the average for this class. If I'm calculating the mean, around 2. Right, maybe a little bit higher, or right around. Well, what could be some biases that exist? If I was using the average kind of response to this question from you guys to make an inference about the population as a whole in the US, why would that be a problem? You're much younger, right, than the average person in the US, right? Yeah.
You have access to like healthy food and places to work out.
Yeah, right. Like you're on a college campus, you're given a lot of resources. The average college student, right, is, not, this isn't true about everyone, right? But on average, if I'm taking a sample of college students, they're going to come from a higher income than those who don't, right? So you access to better foods, things like that. So, right, there's going to be some biases that exist because I over-selected from a certain age group, right? And I over-selected kind of college students, right, versus kind of not. What's some other issues in my list? So what's one bias that I kind of shut down? What's one bias that we talked about that definitely won't exist? Yeah. Yeah, right. So what did I do? There's an incentive to respond because I'm using this as an icon. So what you can do, as long as you create the same incentive for everyone, it's okay, right? I just can't create incentives for certain groups and not others, right? So I can shut down the non-response bias if I can provide incentives to every group, or incentives that would be equally as attractive to every group, right? For instance, when you see, do you guys get these emails for like fill out this survey and you can win whatever? So they're trying to create incentive to increase the response rate, right? But who do you think is more likely to care about that incentive? Someone who is on the lower end of the income distribution or someone on the higher end? $50 gift card doesn't mean much to me if I'm Jeff Bezos, right? Like it's not worth my time. While someone on the lower end, right? So even creating that same incentive doesn't necessarily, like monetary incentive, doesn't necessarily affect all groups equally, and you still aren't really changing that non-response bias. So that's one that we kind of shut down here. Maybe you misunderstood the question, right? Hopefully the person that said 4 thought 4 was the highest. Hopefully that's what it was, right? But so misunderstanding the question. Also, I kind of forced you guys to non-maliciously lie to me, right? Because I only gave you 4 discrete options. Maybe you feel like a 1.5. Well, that's not a possible way to respond. So I forced you to lie to me. Like either if you said 1 or 2, it wasn't truly how you're feeling, right? I didn't make this a truly kind of continuous range. Okay? So anytime you force something to be discrete, you're almost forcing people to non-maliciously lie to you. Right? You're building that into your sample. So you wouldn't want to do something like this. Right? Let's see which other ones I forgot. Oh, people might just lie to me also. Like most people think that they're like not as healthy as they actually are, which is kind of a weird thing. But if you look at the literature, that's generally people like report what their actual health is, just because like mentally they think that they're not as healthy. We talked about the interpretation, kind of the discrete. We talked about kind of this over selection bias. What if I asked you how many alcoholic drinks you had an average each week? With class this small, I won't ask because it's fine. But if I did ask you this, right? So 0, 1 to 5, 6 to 12 drinks, or more than 12. What do you think is true about the average college drinking behavior relative to the population? I was in college once. I'm telling you right now, you don't keep drinking the same way that you do when you're in college. All right. So if I'm over selecting college students here, I already know that my mean result's going to be screwed up. Right? It's not going to match the population. Some other interesting things that would exist in this one, right? You might have people that you still, even though I tried to create a non-response bias by making this, if I did use this as an accurate question, why might I still get this kind of, what could a non-response bias be here? If you think that I'm going to look at the response afterwards and you're not 21, maybe you just don't respond. You might respond 0, right? You might lie, but you also might just not respond, right? So I could still have a non-response bias even when I'm creating these incentives for people to respond. I might have people who over-report, lie to me, right? The one guy at the party who always wants to tell you that you can, drink the whole 30-pack or something on his own, right? Or, right, you might underreport because you're not 21 yet, or you think you're not going to look at the data. Right? So there's all these biases that exist. Like even when we try to shut some of these down, we can't forget, like no matter how good we do it at eliminating our selection bias by doing like stratified random sample or cluster sampling, no matter how much we try to make sure our sample matches up demographically with the population, we're always probably going to have some of these biases existing, and we need to keep that in mind. Anytime we're looking at the results, we're looking at these variables from our sample, these represent, they're just a sample of the population, and they might have these biases built in. So we can make inferences based off of them, but we want to be careful with how much we're using them, right? If we think that some of these biases might be floating around in the background. So we'll think about a lot of these as kind of moving forward. I don't know, this was an example I had at one time, right? This was not for the last selection, but the one prior. All the polls got it wrong, so the 2016 election. And there was this paper, and you kind of went through, and it talked about all these different biases that existed in political polling. So why did all these polls get it wrong? And then think that Trump was going to lose in 2016, and he actually won. So we had a huge selection bias. All right, so a lot of these polling places they're doing a better job now that we have the internet, right? But they still tend to be oversampling people from larger urban areas, right? Which we know tend to be a little bit more democratic, right? So there might have been some of that selection bias that existed, right? But even if we had a really good company and they were aware of this and they made sure that they didn't overselect from large cities, we have that, it tends to be that just more educated individuals are more likely to be involved in politics. And so higher educated individuals, now this is not everyone, I'm talking about averages, right? But the higher your income on average, the more likely you are to kind of be Republican, right? And there's like combinations of characteristics, but in terms of just the distribution breakdown of just income. So, more educated people are a little bit more likely to be involved. We might kind of see it skewed a little bit one way or the other. The non-response biases is really what the paper was, or there's a paper all about this. Is pretty interesting. So who might not respond to calls or kind of these mailers? Well, we just, think about people who have, like I talked about earlier, lower income. So maybe lower income individuals aren't as likely, but we're not thinking about characteristics, right? We're just thinking about kind of maybe like the alcohol example. If I were at the time asking people who they were going to vote for, Trump or Clinton, a lot of the Trump voters maybe felt like they didn't want to respond and tell the person they were going to vote for Trump because there might be some social cost to it, right? They might feel like that person would judge them or whatever. And they actually, they went through and polled a bunch of people who did vote for Trump. And what they found was this was kind of one of the things that was built into these early polls, was that people who ended up voting for Trump were less likely to respond to these political polls, right? So I think they called them like shy Trumpers or something. I had unintended lying, right? At the time, a lot of people were like switching back and forth. And then malicious lying. This was kind of people who knew they were going to vote for Trump, but they were just telling the survey, right, people that they weren't. So one way we can avoid a lot of this, like this article was just, I was kind of going through, was that all this polling is still a lot of it's done by like people calling, just because when you hear someone's voice, it's like personal, so you're a little more likely to actually stay on the phone and just answer a couple questions. Well, the problem is when you hear someone on the other end, you might get some of this malicious lying or this non-response, right? That people like don't want to tell you who they're actually voting for, right? Because they feel like they don't want you to judge them. They don't know what your opinions are. So what we should be kind of transitioning to is something that's like strictly done online. And a lot of people don't like that because, well, you can fake the date. Well, you can put up, different, I'm not a computer programmer, but you can protect this, these websites, and then you kind of remove this personal element where now if I'm just clicking a button and I don't have to like hear someone or see someone, it's kind of reaction to me telling them I'm voting for a certain candidate, you can actually elicit more accurate responses from individuals. So kind of keeping it as little or as impersonal as possible. There we go. Yeah, anonymous or impersonal. Like you don't want to involve kind of these feelings, emotions. You're just trying to elicit what they're actually going to vote for, right? Because that's really what you're trying to do with this political poll is predict, right, what the actual outcome is going to be. We got 5 minutes. So I'll kind of set up what we're going to talk about next class. This was kind of a class where I think it's funner I think it's more fun to talk about, right, kind of some of these biases that exist and start to think about what's going on behind the scenes with statistics, right? We didn't do anything with computation, right? But it's because we're trying to think about the broader picture of what we're trying to do with all these statistics, right? So we're going to take this sample and hopefully we remove as much bias as possible, right? So we're going to have this sample mean. Now, what's going to end up being true about this sample mean is that if we draw samples of different sizes, right, that might make our sample mean more or less useful. If I'm trying to get an idea about what the average income in the US is, and I only take samples of size 1, well, it's actually pretty likely I see a sample mean income from that one person that's very different than what the actual mean is, right? But so like maybe think about it this way, like maybe I take a sample of size 1, I sample someone, I happen to get someone who only makes, or let's say they make $130,000. Well, I know that that's not reflective of the population. I just happen to get someone who's kind of on the right side of the distribution there. Well, what if I sample 100 people? Well, I'm greatly reducing the likelihood that if I randomly sample 100 people, that I'll see a sample mean of 130,000, right? If I have 100 people, yeah, I might have maybe I have a couple people in my sample who are on that higher end of the income distribution, but they're only 1 out of 100, right? So they're not influencing the mean as much as they did when they were the only person in my sample. So taking samples of higher size usually results in us having a more reliable sample mean in terms of being able to make inferences. If we looked at samples of different sizes, right, each sample size, right, the sample means would have a distribution of their own. So when I say the distribution of sample means, I think I'll set this up here and we'll think about this more next class. So I've got this original variable X, and maybe I'm sampling from it. And maybe I take a sample of size 100. I calculate the sample mean. I write that number down. I randomly sample another 100 people. I calculate the sample mean from that group. Write that number down. Randomly sample. I continue to do this process. Eventually, I might have a list of like a couple thousand sample means, right? So let's say I took 10,000 samples, calculated a sample mean from each one. I'd have 10,000 different sample means. Well, if I had that in Excel, I could actually do a histogram. I could look at the distribution of those sample means. So what's going to end up being true is if I do that, my sample means will end up being distributed around whatever the original population mean of the data I sampled from was. So if I look at 10,000 different sample means, and let's say I was calculating the average income from 10,000 different samples, the average of those 10,000 sample means will be whatever the original average kind of income was from that population I was sampling from. So another way we say this is the sample mean will be equal to whatever the mean of my sample means will be equal to whatever the original population mean was from the data I sampled from. And what ends up being true, and kind of have a caveat here, if I take sample sizes over 30, my sample means will always be normally distributed. So that's kind of the central limit theorem. I think we'll talk about that next class. We'll talk a little bit more about kind of what the variance of my sample means is, how that relates back to the original data we sampled from. And I'll kind of show you this like little walkthrough with data where I not just tell you these things, I'll prove it to you with data, right? There's some actual mathematical proofs that use that probability density function of the normal distribution. We don't want to look at that. It's nasty. It's actually difficult to kind of understand as well. But I'll kind of give you these things and then I'll prove it to you with the data, right? That it plays out that way. Okay. So I would start working on that next individual assignment, try to start knocking out as much of those as possible so that as we kind of keep working through things, you're able to finish those up in a short amount of time as we get closer to the due date. Okay. All right. I will see you guys on Friday.